household wiring and electrical safety. Welcome to this presentation on household wiring and electrical safety. Today, we will explore several key topics. We will begin by discussing household wiring systems and how power is distributed. Then, we will look at circuit protection devices, specifically circuit breakers and fuses. Following that, we will examine electrical safety, focusing on the dangers of short circuits. We will also explain the importance of grounding and the function of three-pronged plugs. Finally, we will conclude with an overview of ground fault circuit interrupters, commonly known as GFCIs, and how they provide critical protection against electrical shocks. Let us start with the basics of household wiring. Utility companies distribute electrical power to our homes through a pair of wires that are connected in parallel. One of these is called the live wire, which has an electric potential that oscillates relative to the ground. The other is the neutral wire, which is grounded and has an electric potential of 0. The potential difference between these two wires is approximately 120 volts. As the power enters the home, it passes through an electrical meter that measures the consumed power in watts. The diagram illustrates how the live and neutral wires form a parallel circuit, providing a constant 120 volts to various appliances, represented here by resistors, with a circuit breaker in place for safety. Now let us discuss circuit protection. As power enters the house, the electrical meter is connected in series with the live wire to accurately record the total energy consumption. After the meter, the wiring splits into multiple parallel circuits, each protected by a circuit breaker or a fuse. A circuit breaker is a special switch designed to automatically open and break the circuit if the current exceeds a specific rated value, such as 20 amps or 30 amps. This mechanism is crucial because it limits the current and prevents the wires from overheating, which could otherwise start a fire. In a typical home, each major circuit is equipped with its own dedicated breaker to provide localized protection and ensure that an issue in one area does not shut down the entire house. To understand why a circuit breaker might trip, we can calculate the load and current for various appliances. The current drawn by an appliance is calculated using the formula: power equals current times the change in voltage. Let us look at a standard 120-volt circuit. A 1,000-watt toaster draws 8.33 amps of current. A 1,300-watt microwave draws 10.8 amps. An 800-watt coffee maker draws 6.67 amps. If you were to turn all three of these appliances on at the same time, the total current would be 25.8 amps. If this specific circuit is protected by a standard 20-amp breaker, the combined current will exceed the limit, causing the breaker to trip and preventing the appliances from operating. While standard circuits use 120 volts, heavy-duty appliances like electric ranges and clothes dryers require more power and operate on a 240-volt system. To provide this higher voltage, the power company supplies a third wire that is maintained at a negative 120 volts relative to the ground. By connecting an appliance across the standard live wire at positive 120 volts and this third wire at negative 120 volts, the total potential difference becomes 240 volts. Operating at this higher voltage allows these heavy-duty appliances to draw half as much current as they would at 120 volts, meaning smaller wires can be used safely without the risk of overheating. Moving on to electrical safety, let us discuss the hazard of short circuits. A short circuit happens when there is almost zero resistance between 2 points that have different electrical potentials. This lack of resistance results in a very large, dangerous surge of current. Normally, a circuit breaker will open to prevent damage. However, a serious danger exists if a person touches a live wire while they are also in contact with the ground. For example, touching a frayed cord while leaning on a water pipe or standing with wet feet completes the circuit through the body which can cause severe electrocution. It is important to remember that normal water is a good conductor of electricity due to the ions from various impurities, making wet environments particularly hazardous. To protect against electric shock, modern electrical outlets use three-pronged cords and plugs. The first two prongs are the live wire at 120 volts and the neutral wire at 0 volts. The third prong connects to a safety ground wire. Under normal conditions, this ground wire carries no current and is connected directly to the metal casing of the appliance. If an internal fault occurs, such as a live wire accidentally touching the inside of an electric drill's metal case, the case becomes energized. Without a ground wire, the person holding the drill would act as the path to ground and receive a shock. However, with the safety ground wire in place, the drill case remains at ground potential, and the dangerous current is safely redirected away from the user. In addition to ground wires, ground fault circuit interrupters, or GFCIs, are crucial safety devices. These are specialized outlets installed in high-risk areas where water is present, such as kitchens, bathrooms, and exterior locations. A GFCI works by constantly monitoring the circuit for very small leakage currents, as low as 5 milliamps, that are escaping to the ground. If it detects this leakage, which could indicate a current passing through a person, it shuts off the power in less than 1 millisecond. This extremely fast reaction time prevents fatal electric shocks. GFC is provide a layer of protection against hazards where traditional circuit breakers would be far too slow or entirely insensitive to the small currents that can cause harm. It is important to understand the physiological effects of electric shock. The damage caused depends on the magnitude of the current, how long the exposure lasts, and the path the current takes through the body. Even very small currents can be dangerous. A current of 5 milliamps or less will cause a sensation of shock, but typically results in little to no damage. However, if the current exceeds 10 milliamps, it causes involuntary muscle contraction, meaning the person may be physically unable to let go of the live wire. At approximately 100 milliamps, the shock can be fatal as it paralyzes the respiratory muscles and stops breathing. A current of around 1 amp can produce serious or fatal burns. As a general rule of thumb, no bodily contact with electrical wires is considered safe if the voltage is greater than 24 volts. To summarize our discussion, household electrical systems are designed to connect appliances in a parallel configuration. This ensures that a constant 120 volts is maintained across each device. We use circuit breakers and fuses to protect the home's wiring against excessive currents, which prevents overheating and potential electrical fires. Furthermore, safety ground wires and ground fault circuit interrupters provide critical protection for individuals. They work by either safely diverting leakage current or instantly cutting off the power supply to prevent electrocution. Finally, we must respect electricity, as the severity of an electric shock scales rapidly with the magnitude of the current, and even brief exposures to relatively low currents can be life-threatening. Let us conclude with a couple of review questions to test your understanding of the material. First, think about the wiring configuration in a home. Why are household appliances connected in parallel rather than in a series circuit? Consider what would happen to the voltage and functionality of other appliances if one device was turned off in a series setup. Second, explain the safety mechanism of a three-pronged plug. Specifically, how does the third safety ground wire prevent you from receiving a dangerous electric shock if a live wire inside a power tool accidentally comes into contact with the tool's outer metal casing? Take some time to review these concepts, and thank you for watching.